Good morning, friends. I am Dr. G.S. Raghuvanshi. We will be discussing the phenomena of interference of light today. As the word speaks, the subject comprises of two words, namely interference and of light. Interference is a general term used when the waves superimpose. A common example is, suppose two persons are talking and a third person speaks in between. It is obvious that they will not understand what other has spoken about. Obviously, we say that the sound waves or the speech emitted by the two have interfered with the third wave. In physics, in general, we talk of interference as a special case of superposition of waves. Interference is the property of wave motion. All types of waves interfere. We will be discussing what interference is and how the interference of light differs from interference of other waves. In general, when the two waves meet at a point at the same time, the two waves disseminate themselves, disappear their identity, and new wave is formed. We say that the waves have superimposed. The important thing here is that the two waves are meeting at a point at the same time. In mathematical words, the x and t are same for both. Generally, wave is a periodic disturbance. And when we talk of periodic disturbance, in mathematical terms, we write periodic disturbance in terms of sine and cosine. So, a wave must be a periodic function of x and t. And the simplest periodic function in x and t we can write is where A is the amplitude which is related to energy, K is propagation constant, it is related to wavelength, and omega is angular frequency, it is related to frequency by a constant factor 2 pi. This is a propagating wave. Here, this entire angle is known as phase, and the constant here refers to amplitude. So, you see there is a periodic variation in the disturbance with x and t. So, it represents a wave. If it is an electromagnetic wave, the disturbance is nothing but of electromagnetic fields. If it is a mechanical wave, the disturbance is mechanical sound wave, and if it is a matter wave, the disturbance is nothing but the probability disturbance. So, in general, wave has got this type of structure. When we talk of superposition, then suppose we have got two waves, namely psi 1, A1 sine, K1x, omega 1t, phi 01, psi 2, A2 sine, K2x minus omega 2t plus phi 02. Phi 01 and phi 02 are initial phases of the waves. omega t minus kx plus phi is the phase of a wave in general. When we talk superposition of waves, then what we see, psi is equal to psi 1 plus psi 2. To find this addition of two waves, we represent wave in a phasor form. How do we represent a wave in a phasor form? This will be clear from the following diagram. Suppose we take x axis as the phase axis and y axis as the disturbance axis, and we draw a vector of length a, making an angle phi, that means phi is the phase of the wave. We correct this here, it should be phi 0. To write the complete phase phi, this I write as phi 0, so this phase in short I can write as phi. You see, the projection of this onto y axis is nothing but a wave. This is the phasor representation of a wave. Any wave can be represented by a vector of amplitude a, making an angle equal to phase of the wave. The phase comprises of a time term, a space term, and an initial phase. Okay. Then, to find out the resultant wave on account of superposition of two waves having amplitude A1 and A2, phases phi 1 and phi 2, we use vector addition, and the resultant wave amplitude is obviously given by A square, A1 square plus A2 square plus twice A1 A2 cos phi 2 minus phi 1. It is quite clearly seen in the diagram. Now, the intensity of wave is nothing but the energy propagating with the wave per unit area per second. The energy of simple harmonic motion is simply half m omega square a square, and therefore intensity is directly proportional to amplitude square. Therefore, the resultant wave intensity I can be written as I1 plus I2 plus twice square root of I1 I2 cos delta phi, where delta phi is nothing but phi 2 minus phi 1, and in explicit form it is k2 minus k1 into x minus omega 2 minus omega 1 into t plus phi 01 phi 02 minus phi 01. See that resultant wave intensity I varies periodically with phase difference delta phi. We can easily say, if I is equal to I1 plus I2, the two waves do not lose their identity, they can be separately identified, and in this situation there will be no interference at all. And therefore, for interference to occur or superposition to occur, I must not be equal to I1 plus I2. This sets a condition here that this implies delta phi must not vary with time. If delta phi varies with time, the periodic variation intensity with the space and time will continuously change, and average effect will be nothing but the identification of two independent waves, and therefore there will not be any interference if I is equal to I1 plus I2. Therefore, we can easily say that this term, the last term in this equation, is the interference term or superposition term. So, to observe interference, this term should not be, cos delta phi should not be equal to 0. That is the condition for superposition. Let us see what happens. Let us examine what are various forms of superposition, what are the various conditions in which they occur. Let us station at a point so that x is fixed. When x is fixed, the intensity varies periodically with time. Intensity varies periodically with time with the difference in frequency of the two waves. This phenomena called interference in time and sometimes referred as the formation of beats. This phenomena is very important in the detection of high frequency waves. Our target is something else. Suppose we choose that the frequency of the two waves is the same. So, when we consider the superposition of the waves having same frequency, then intensity varies periodically with distance, space. This phenomena is called interference. And therefore, here is the definition of interference. When the two waves of the same frequency superimpose in a space, the resultant wave intensity varies periodically with the space, then we call this interference of waves. The observance of the interference of sound is very common, but to observe interference of light, some more important things have to be worked out. Because number one, light is a transverse wave, and second, the frequency of light is very high. It is of the order of 5 into 10 raised to the power 14 hertz against sound whose frequency is just 20 to 20 kilohertz. See, this makes a big difference, because under normal conditions, these frequencies can easily be heard by our ear, but in order to observe light of this frequency, we observe many waves at a time. And when we observe many waves at a time, there are many interesting phenomena that are occurring. Let us see what are those phenomena which are occurring. But before this, we can set out the conditions for observing interference. Conditions for observing interference. Sustained interference. The first condition, as we have already spoken, is the frequency of the two waves must be the same. Second important condition laid down here is that phase difference delta phi must remain constant in time. Otherwise, the intensity of the resultant wave will continuously change and average effect is nothing but uniform illumination. See, delta phi constant implies that phi 02 must not change with time. The phase difference of the two waves remaining constant in time refers to that the waves are coherent. So, the essential condition for observing interference of light is that waves must be coherent. That means the phase difference between the waves must remain constant with time, because if it varies with time, omega 2 minus omega 1 into t, this term will continuously vary with time, and the cos average of delta phi shall become 0. Average of cos delta phi will become 0. Cos of delta phi average becomes 0 if phi varies with time. Let us see what is its implication physically. Light is emitted when an electron transits from higher state to lower state. As a consequence, it emits light in terms of a photon constituting some number of waves. Also, we call this as a wave train. When another photon transits from higher state to lower state in the same atom, it emits another wave train. So, a light ray consists of large number of intermittent wave trains, and the phase difference between these wave trains vary randomly with time. Phase difference delta phi varies randomly with time. Consequently, you can easily think that if we take an ordinary light which consists of large number of intermittent pulses, then the two component light cannot undergo sustained interference. To observe the condition of coherence, that means delta phi remains constant in time, we have to confine on a single wave train. We have to confine on a single wave train. Then and then only coherent waves can be obtained and they can be put to interfere. There is an exception here. If we use laser, laser by definition is a coherent wave train. Large number of wave trains are coherently added in a laser, and therefore it is possible to observe interference in two phase log lasers, but it is not possible to observe interference between two ordinary light rays. So, what to do now? The answer is very simple. In order to observe interference of light, we have to divide this wave train into two parts, either through amplitude or through phase, either phase division or amplitude division. Then the two waves will interfere. All the experiments where we observe interference either use the division of wave train or division of wave front. So let us summarize the conditions for observing interference. The conditions are: number one, the frequency of the two waves must be the same. Not nearly the same, must be the same. The second, the phase difference between the waves must remain constant with time. That means waves must be coherent. There is a third important condition. Light is a transverse electromagnetic wave, and therefore, if the polarization of two waves are mutually perpendicular, thus there cannot be any superposition. As a consequence, third, polarizations of the waves should be the same if polarized. These are the three essential conditions for observing interference. However, because interference is put to use experimentally, therefore, it sets few more conditions for observing good contrast. There will be very good contrast when maximum is most bright and minimum is most dark. Therefore, this sets a condition that the amplitude of the two waves must be the same. And second, they should have same polarization. Third, they should be propagating approximately in the same direction. So this is the summary of the conditions for observing interference. I repeat it. The frequency of two waves must be the same. The phase difference between waves must remain constant in time. That means waves must be coherent. Third, if polarized, the polarizations must be the same. For good contrast, the intensity or amplitude of the two waves should be the same, and they should be propagating almost in the same direction. Under this condition, we will observe best interference, best sustained interference rather. As I have pointed out, to observe interference in ordinary light, we have no option but to divide the wave train, either amplitude wise or phase wise or wave train wise. I give two experiments in which this is observed. First, wave front division. The best example, Young's double slit or biprism. See, we take a single slit. This slit is very fine slit, and we put two slits which are almost identically placed, and we put a screen here. The wave fronts propagate, and since the two slits lie on the same wave front, the secondary sources formed are coherent sources, and therefore we shall observe interference of light. This is division of wave front. In case of amplitude division, we use the phenomena of reflection. Let us consider a thin film. When light is incident, a part of light is reflected from the first layer because whenever wave finds a discontinuity in the medium, a part of wave is reflected, and therefore a part is reflected from here and another part is reflected from the lower part. These two, waves reflected from the upper layer and wave reflected from the lower layer, they form two coherent waves, and these will interfere. The examples are many. One example of amplitude division is Newton's rings. We have got a plain glass plate, and onto it we put a plano convex lens. Plain glass plate, and over it we put a plano convex lens. So there is a thin film formed here. Light when incident, a part of light is reflected from the upper boundary of the thin film and another part of light is reflected from lower boundary. These 1 and 2, they are amplitude divided coherent beams and therefore will undergo interference of light. Similarly, we have another experiment, Michelson's interferometer. Michelson's interferometer. In this, a light traveling falls on a beam splitter which splits light into equal amplitude waves, and these travel in mutually perpendicular directions because the beam reflector is put at an angle of 45 degree. So the two waves travel amplitude divided two wave trains, they travel mutually perpendicular. But there cannot be interference in the light which are traveling mutually perpendicular. So we put two mirrors which are normal to these waves and they reflect the waves back to combine at the beam splitter. Like this, mirror M1 and mirror M2. They are put perpendicular to this and therefore the waves get reflected back, and we observe through telescope the interference produced by two beams. This is the underlying principle of Michelson's interferometer, where we use division of amplitude. The division of wavefront is used here. One interesting thing is, suppose we remove this slit, here is a sodium lamp, suppose we remove this slit and try to observe interference between the two slits S1 and S2, the interference will disappear because the two beams traveling are no more coherent. This is the demonstration that coherence is a must to observe interference of light. Summarily, this is the background of interference of light. What are the conditions to observe interference? Number 2, what are the requirements? Number 3, how do we observe interference of light? Now, we select the specific experiments to discuss the interference of light in detail. Let us come to Newton's rings. Newton's rings are the interference rings observed by Newton. That's why they are known as Newton's rings. Newton's rings are formed because of division of amplitude. See, suppose we have got a thin film and light is incident normally onto the film. one part of light is reflected from the upper part because there is a air film interface, and another part of light is reflected from film air interface second. Therefore, there are two waves which are amplitude divided coherent waves. The path difference between the waves, is obviously 2t, and because there is a medium, so this is the refractive index of the medium. Path travelled in air is 2t. If the refractive index of medium is mu, the effective path will become 2 mu t, and therefore, the path difference between waves 1 and 2 is 2 mu t. Let us come to the basic interference term. I is equal to I1 plus I2 plus twice square root of I1 I2 cos delta phi. See, if cos delta phi is plus minus 1, the intensity become maximum, and the maximum intensity is just on the other hand, if cos delta phi is minus 1, cos delta phi is plus 1, plus 1, then this is this. If it is cos delta phi is equal to minus 1, the intensity becomes minimum intensity, and it is just equal to so the phase difference determines whether the intensity will show a maximum or a minimum. So let us find out further. For maxima, delta phi must be equal to 0, 2 pi, 4 pi or 2n pi. For minima, delta phi has to be pi, 3 pi, 5 pi and so on, 2n minus 1 into pi. This is the phase difference. The corresponding path difference, delta is lambda upon 2 pi into phase difference, and therefore, the corresponding path difference for maxima, it comes out to be 0, lambda, 2 lambda, n lambda. Whereas for minima, it will come out to be delta lambda by 2, 3 lambda by 2, 5 lambda by 2, n minus half into lambda. These results, mathematical results, are very easy to understand if we see the superposition of waves physically. For example, if one wave is this, another wave superimposes with a path difference of lambda by 2, what is happening? The resultant wave amplitude is simply A1 minus A2. So this is destructive superposition or destructive interference. On the other hand, if the two waves superimpose like this with a path difference of lambda, the amplitudes are added up. So this is constructive interference. A is equal to A1 plus A2. And therefore, it is the path difference that determines the resultant intensity, whether it is maximum, minimum or in between. Therefore, if we take this path difference, the normal incidence of a wave in a thin film the path difference is twice mu t. This is the geometrical path difference, however, because we see that wave 1 is reflected from air film interface. Wave 1 is reflected from air medium interface, that is, it is reflected from the denser medium, and therefore wave 1 suffers a phase difference of pi or corresponding path difference of lambda by 2. Therefore, the optical path difference is simply twice mu t plus lambda by 2. That is the optical path difference. Suppose the wave is incident at a certain angle instead of normal. We just see that only a component of wave which will fall perpendicular to the film. Since a component falls perpendicular to the film, the optical path difference in this case will simply be twice mu t cos r, where r is the angle of refraction, plus lambda by 2. This is in general the path difference when there is a oblique incidence. In case of normal incidence, the path difference is simply twice mu t plus lambda by 2. In case of oblique incidence, there will be additional factor of cos r, where r is angle of refraction. So obviously, we shall find maximum of intensity when twice mu t plus lambda by 2 is just equal to n lambda, or twice mu t is just n minus half into lambda, or the thickness of the film t is simply n minus half lambda upon twice mu, in case of the film has a refractive index mu. So what is the conclusion here? The conclusion here is that it is the thickness of the film that determines the interference intensity. It will be maximum when thickness corresponds to this, and the thickness corresponding to minimum will be simply n lambda upon 2 mu. We can obtain maximum to minimum and minimum to maximum by adding a path difference of lambda by 2. As clear from these diagrams, if a path difference shifts by lambda by 2, maxima is changed to minima and minima is changed to maxima. Therefore, coming to Newton's rings, Newton's rings are observed when a plano-convex lens is put over a plane glass plate. Plane glass plate means optically plane glass plate. We consider the incident light. A part of light is reflected from the lower face of the plano-convex lens, and another part of light is reflected from the front face of the plane glass plate. These 1 and 2 are amplitude divided coherent waves, and therefore they will undergo interference. See that the result of interference is divided by film thickness here. If it corresponds to this relation, we will observe maximum, and if this corresponds to this, we will observe minimum. Now, interesting thing is, Since plano-convex lens has been put on a plain glass plate, so this thickness, whatever is the thickness here, this thickness is same throughout the circular section of the film, throughout the circular section of the film. If you view it three-dimensional picture, the thickness is same here and entire thickness is same everywhere on the circumference of this circle. Since the locus of the thickness is a circle, that means maxima and minima have locus to be the circles, and therefore the interference pattern will consist of circular rings, concentric circular rings. I repeat, since the thickness remains same on the circumference of a circle, therefore the interference fringes will be circular. These circular fringes are known as Newton's rings. Since their radius depends on thickness, radius of this ring depends on thickness, and thickness continuously varies from 0 to a certain value. Therefore, various interference rings will have different radii and they will directly related to the thickness of the film. And therefore, measuring radius of these rings, we can measure the wavelength of light. Let us see how the radius of the film varies with thickness. Let us now find out how radius of the film, radius of the ring, Newton's ring, is related to thickness and subsequently with the wavelength. So, see, we are considering the ring corresponding to nth bright ring, corresponding to thickness Tn bright. It is clear from this diagram that thickness Tn bright will give me nth bright ring here. Obviously, Rn bright is simply equal to square root of Pythagoras theorem. Simply, this square is equal to this square minus this square, and therefore Rnb whole square is just equal to R square minus R square plus minus Tn bright square plus twice R Tn bright. R square and R square cancels. Tn is quite small. Therefore, Tn square is almost negligible. We therefore have Rn bright simply under root twice Tn bright. Since Tn bright is here n minus half lambda upon 2 mu, we can substitute this here, and we have the radius of bright ring nth bright ring is, we substitute the value of 2Tn, this is equal to n minus half lambda r upon mu. And similarly, Rn dark will be simply n lambda r. See that when n is equal to 0, Rn dark goes to 0, but Rn bright does not go to 0. And therefore, the center of Newton's rings will always be dark. Repeat, the center of Newton's ring shall always be dark. This can also be physically understood. How? At the center where plano-convex lens touches the plane glass plate, the geometrical path difference is 0, but the optical path difference is lambda by 2, and therefore net path difference is lambda by 2, making the waves to destruct themselves, and therefore center is dark. See here, there is a simple relation between the radius and the wavelength. If we can measure the radius of the ring, we can calculate the wavelength of light. However, the radius of Newton's ring is not measurable because the central bright spot is quite thick and it is difficult to ascertain the center of the central ring. Therefore, alternately, we measure the diameter of the ring. So, diameter of say nth dark ring, diameter of nth dark ring, it will be simply 4n lambda r. We can similarly write the diameter of n plus mth ring and square it. We will be getting 4n plus m lambda r. We can find this relation n plus m whole square minus dn square is 4m lambda r. From this equation, we can easily calculate the lambda dm plus n whole square minus dn square upon 4m r. Please be careful that I have avoided the refractive index here. I have not included refractive index here. That means I am dealing with the film in air. Film in air. If I deal with film in a medium of refractive index mu, then there will be a factor of refractive index mu. Therefore, in a laboratory, we can measure wavelength of light by measuring the diameter of the rings. Diameter of n plus nth ring and nth ring, squaring them, finding out the difference, and we can compute the wavelength of light. Let me discuss it little bit in detail. Suppose this is a Newton's ring system. Since we are measuring wavelength of light which is of the order of 10 raised by minus 7 meters, therefore the measurement has to be very precise. In all the electronic instruments and the mechanical instruments which are moved by a micrometer screw, there is a backlash error, and backlash error is of the same order as wavelength of light. Therefore, it is advisable to move the micrometer screw only in one direction. I repeat, for the entire experiment, the micrometer screw has to be moved in a single direction. Therefore, what we do? We first set the crosswire at the center of the ring pattern. Then we move towards the left by counting the rings, say first ring, second ring, third ring, fourth ring, fifth ring, and so on and so forth. Ultimately, we go to say 21st ring. And now we come back to 20th ring by moving it towards right and write down in the notebook that we are moving the micrometer screw towards right. Then we go to 20th ring. We take readings up to say 5th ring and stop taking reading because the thickness of Newton's ring goes on decreasing as we increase the order. That means the initial rings will be quite thick and it will be difficult to put the cross wire at the middle of the ring, and therefore all the experiments, all the observations are taken at higher order rings, that is beyond say 5th ring. We come to the next side and start taking reading from 5th to say 20. The experiment is complete. We subtract the reading of 20th on one side and 20th of the other side, that gives diameter of 20th ring. Similarly, we subtract the value position of 19th ring on the two sides, we get diameter of 19th ring, and so on and so forth. So, using this information here, 20th ring and 5th ring, the formula can be modified. Lambda, this is d20 square minus d5 square, and obviously m here becomes 15. Radius of curvature of plano-convex lens is determined by spherometer, and we can compute wavelength of light. Gentlemen, there are few sources of error here. Before starting the experiment, one has to ascertain that the center of the ring pattern is dark. If center of ring pattern is not dark, this implies there is some dust particle between the center of the lens and the plate. So, the advisable thing is they have to be cleaned by spirit and put again, or as a usual practice, we have to slightly disturb the lens so that it goes away from the particle and central dark ring is formed. Then we take the observation from one side of the ring pattern to the other side of the ring pattern, moving the micrometer screw only in one direction. We can use the formula to determine wavelength of light. If we want to determine the refractive index of the medium, then we have to repeat the experiment 2 times, one with film of air, another time we take a syringe, medical syringe, take out liquid and spray it in between here. Obviously, ring pattern will shrink. Diameter is inversely proportional to the square root of refractive index. Therefore, rings will shrink. We can measure the difference in the diameters of the two rings and use the formula to determine refractive index. And we can easily determine the refractive index of a liquid. In engineering, there are refractometers which use this concept. They spray the liquid in half of the section of the lens, and therefore the rings shrink in diameter. They compare the diameter of n ring and n plus nth ring, and there is a comparator and a programmed IC that directly gives the reading, and thus a refractometer is formed.